Everyone who has joined us. We'll start this session now. Hi everyone, I am Uttara from Technology Office team and I welcome you to this session. Today we are presenting a webinar on ML Model Lifecycle Orchestration using Dyna.MLOps open source framework by Next.ai COE. So before we move on to the session, I want to present in Spotlight today the Next.ai page, which is available on our knowledge portal Accelerator. And here you can easily access and understand the clear articulation of our current analytics and AI capabilities with your stakeholders. The page showcases Next.ai Lab, multiple solutions, case studies, webinar repository, and much more. So do leverage this information. Moving on to session guidelines, audience will be muted while the presentation is on. You can continue to post your questions in chat and COE experts will be answering them. We will also have a live Q&A with Shreyas post this presentation. As always, the PDF and recording will be made available on Accelerator and I'll be sharing the links in the chat window. In case you are planning to leave this session before conclusion, please do give us feedback. We will be sharing the feedback link in the chat too. So let's start with today's presentation where Shreyas is going to cover ML model lifecycle orchestration using this Dyna.MLOps open source framework. Shreyas, please start the session.
Yeah, thank you, Uttara, for the introduction. Hi, good evening, everyone. My name is Shreyas. I have experience on machine learning, deep learning, NLP, as well as MLOps. I have worked on several industrial projects related to predictive maintenance, model quantization techniques for edge devices, and also AI-based automation for VA and virtual reality-based devices. I have also published a few research papers in international conferences and journals. Yeah, so in this session, initially I'll set the context by talking more about what is MLOps and its relevance in the current industry. I'll also talk about challenges while building or integrating different components in machine learning model pipeline as well as in production. Later on, I'll also show the Gartner's hype cycle for the year 2021. And I'll also list some of the available open source and managed tools for MLOps. Later, I'll describe the Dyna.MLOps open source framework in detail. I'll be touching upon the architecture and various tools or technologies used from experimentation stage till production. At the end, I'll be giving a demo of this framework for an internal use case. Yeah, so moving ahead, this is a slide describing what is MLOps. So MLOps tries to unify or bridge the gap between ML model development as well as the deployment, which we are referring it as operations in this particular slide. So we continuously streamline the delivery of ML models at production using the MLOps features. So it requires coordination among data engineers, data scientists, as well as DevOps engineers to build a complete MLOps pipeline. So as shown in this diagram, so you can easily see what all individual components MLOps include. So the first stage is experimentation stage, where once we formulate the business goals and objectives, we try to gather the data as well. We try to experiment on different kind of architectures or machine learning or deep learning models. So this will be the experimentation stage. So later on, once we achieved the target metrics based on hyperparameter tuning in the experimentation stage, we later move on to the deployment stage. So here, let me open the laser pointer. Yeah, so in the second phase here, as mentioned, as a deployment phase. So here the CI/CD part will happen, the continuous integration and continuous deployment. So our ML model which we have finalized, will be integrated to the source code version control as well as data version control. And we do the continuous integration and continuous deployment in the second phase, where we accumulate all the dependencies and package our particular ML project, which is ready for deployment into production. So the third phase is the operations. So once the model is into production, so it is very important for us to get the feedback on how the model is performing in production. So we keep a check on continuously monitoring the model's predictions when it is in production. So that is the monitoring, continuous monitoring part that has been mentioned in this particular slide. So at the bottom, we can see the same things, the data which is getting gathered for the experimentation stage. So there are three different set of teams that are working in this whole MLOps life cycle. One is the data engineers, who will be having the track of all the data that is being gathered for the ML project. So the data ops will be controlled by the data engineer. So later on, so feature store serves as an intermediary between the data engineer as well as the data scientist. So data scientist will gather, he'll collect whatever the data that has been merged by the data engineer, and he'll do the feature engineering and also build the models accordingly in the experimentation stage. So here we have the data which is getting versioned, as well as the code which is getting versioned from the data scientist as well as the data engineers. So later on, it is moving into the CI/CD platform. That is a deployment phase. Once the model has got trained and validated, and once we do the CI/CD, once it is into the production, we do continuous monitoring of the ML model in production. Yeah. So on an average, it takes about 6 to 8 months to get an AI model integrated within a business workflow, and for it to deliver substantial value. So basically, MLOps reduces the time it takes to move AI models from pilot phase to production phase with a principled approach to ensure high degree of success. So as I mentioned before, MLOps would also establish collaboration and communication communication among a diverse set of teams. That is data engineers, ML engineers, and DevOps professionals. And it keeps track of the business goals or objectives that we have defined before. So the market of MLOps solutions is expected to grow by $4 billion by 2025. And MLOps market consists of at least two open source solutions and at least 18 plus commercial vendors for MLOps. So till now we understood what is MLOps and its importance. So let's now understand a bit on current challenges faced in model building pipeline. So as mentioned in this picture, we can see data science teams, they spend most of their time on data wrangling, data preparation, and managing the software packages, the dependencies that we want in order to get it deployed in production, and also managing the infrastructure, the permissions and all. So usually around 60 to 80% of the time is spent on data as well as the infrastructure management. And only about 10 to 20% of the data scientists time is spent on actual coding or model development. So building a good ML model is just the first step in a very long process of bringing it into production. So bottom, we can see the same depicting the time spent by a data scientist. So in the development or experimentation stage, as I mentioned in the previous slide, he is just spending a matter of weeks to develop the models. And in the right side, we can see a large set of teams are involved. That is data scientists, data engineers, and DevOps engineers. So they will be managing the packaging, scaling of the model, and also if GPU requirements are necessary for inferencing, so even those need to be arranged for production. And once it is deployed, we need to continuously monitor it. We need to parse the logs to fix all the errors. So all these need to be managed. Apart from this, even the CI/CD workflows, the rolling upgrades, all these needs to be integrated in this ML pipeline. So these are the current challenges which everyone is facing. So in this slide, I'm going to talk about some of the challenges that are being faced in production of ML models. So first, the first challenge that I'm going to talk about is the distributional shift. So one of the main reasons for model accuracy degradation that happens over time is due to the change in input feature distributions for which model has not been trained with. Therefore, it is very important to investigate and identify the root cause of data drift by inspecting feature level metrics. The second challenge is the under specification. So as most of you would be aware, in deep learning, the weight matrices, biases, and activation functions, these would be initialized based on some distributions to ensure smooth flow of gradients while training process. So with different random seeds, the underlying random number distributions would tend to vary, due to which models tend to converge differently. So due to this, the model can behave differently on real world data. The third challenge is, so right now, all these years, the approach in any ML based project was mainly model centric. So even if you can recollect, all the research that has happened was model centric, like the architectures that have been evolved in the past 8 to 10 years. So everything was mainly focusing on the model architecture and the training approaches. So here more focus is being given at finding the right model architectures and training approaches. But since data is the fuel for any model, it is equally important to enhance the data to improve the overall performance. So about 99% of research papers that are getting published every year, these are like model centric, and only about 1% contribution is made at improving the data. So there are several aspects where we need to move from the approach of model centric to data centric. So the volume of the data is very important. Obviously, the more amount of data is the only solution to address the bias variance problem for any deep learning neural network based problem. The second one is the annotations consistency. So if there is any inconsistency while annotating the images, suppose, it can completely derail the model. And the third one would be the data quality. So the data augmentations, we can use it to avoid spurious correlations as well as the lack of variations. So in the table mentioned below, we can see in the model-centric approach for steel defect detection based use case, the baseline is 76.2%. So later on, since there were some enhancements done on the data side, the final accuracy has increased about 17%, reaching to 93.1. So there is a marginal improvement in the last surface inspection based use case. So this essentially tells us to move from a model centric approach to data centric approach. Yeah, so now I'll talk about the hype cycle. So the hype cycle would usually help us to keep a track on technology maturity and its future potential. So whenever a new technology is introduced, it would enter the innovation trigger phase, and which is mentioned below in the hype cycle. So as time passes by, the expectations on the technology, it would tend to increase and it would reach the peak of the hype cycle. So here you can see the peak of inflated expectations. So later on, a technology would enter the phase of the trough of disillusionment if it is not meeting up to the initial expectations it had made in the first two phases of the hype cycle. And this is a phase where a lot of questions get arised on the viability of a particular technology in the market. And in this phase, a lot of rigorous testing is tried upon in various R&D phases. Later on, in the last two phases, that is a slope of enlightenment and plateau of productivity. So larger adoption of the particular technology will happen in the last two phases, since it has surpassed the durability test in the trough of disillusionment phase. And this is where the technology gets matured and is largely adopted in the mainstream or the widespread adoption. So as we see this particular curve, the new ML platform functionalities such as model ops, feature stores, reinforcement learning have been introduced in the current year's hype cycle. These ML technologies are still immature and are not ready for mainstream or massive adoption. The model ops covers the broader umbrella of AI models, including graph neural networks and reinforcement learning based models as well. So here you can see MLOps has entered the peak of inflated expectations right now. So in the year of 2019, it was actually in the innovation trigger phase. So right now we can see the introduction of model ops in the innovation trigger. So model ops is almost similar to MLOps, but it is mainly including the whole AI based umbrella, which are having the recent quantum computing, reinforcement learning, as well as graph based neural network models. And as I mentioned before, like MLOps has matured over time and is currently being adopted by many companies. Coming to the MLOps market trends, as mentioned in these two pictures, we can see the Asia Pacific region has more market share in the forecasted period, that is from 2020 to 2027. MLOps has been adopted across various industrial sectors such as banking, healthcare, and pharma. So in this table, we can see the number of companies that have been surveyed and how many are using ML as well as MLOps. So in healthcare as well as banking, automotive, we can see there is a large adoption of ML as well as MLOps. And talking more about the market trends, so here we can see this is information that has been collected from recent reports on MLOps. So continuous training and continuous monitoring are the main focus areas for the particular year 2021. So here you can see the comparison between the previous year and the next year. The continuous training as well as the model monitoring, we can see there is a large spike in the year 2021. That means there is a large interest shown by the community towards continuous training and model monitoring in production. And here I'll be talking about some of the use cases in healthcare as well as financial sectors which have already implemented MLOps. The first one is Florence. So Florence is a healthcare chatbot which reminds the users to take medications and also is able to answer medicine specific information. So this is mostly the patient management kind of a chatbot. So it uses MLOps to establish communication between the ML models, the chatbots, as well as the CI/CD operation tools. The second one is J&J. They have used MLOps to improve forecasting in its vision care business by predicting how many customers would need each product that are the contact lenses to efficiently manufacture according to people's demand. The third one is TMNL, which is a collaboration of five Dutch banks. So it uses MLOps as a standard practice. It deploys AI and ML models to monitor payment transactions for signals that could indicate money laundering or financing of terrorism. And the last one is Sevo. It is a fintech company which applied MLOps to one of its banking customer to deploy and maintain multiple ML models to detect and prevent fraud. And they were able to reduce the time to train and deploy the ML models from months to days. So as we can see from the last use case, there is a large decrease in the time that a particular team would spend by using MLOps when compared to the traditional approaches which were being used before. So these are some of the open source or managed MLOps tools. The first one is Algorithmia and Value High. The first two are managed enterprise grade tools that are available for MLOps. So these, the Algorithmia, it provides security and governance across data models, as well as it provides deployment infrastructure. It also provides reporting and monitoring tools to improve performance and compliance. Coming to Value High, the features that it provides is the version control, experiment comparison, and tracking. And also it provides a model traceability. So where we can know the information that what kind of data and code went into a particular model. And we can also reproduce a particular model experiment. So the third one is Kubeflow. So Kubeflow is an open source project. It is mainly used to build the ML pipelines like the data validation, pre-processing, training, evaluation. So all these steps can be built as a pipeline, and they can be executed on Kubernetes platform. Similarly, the last MLflow and Converge.io. So Converge.io is managed as well as open source. So limited features are available in the open source version. So in Converge.io, so most of these managed as well as open source tools, they mainly focus on the version control, experiment tracking, deployment, as well as the infrastructure that is required to deploy a particular ML model into production, as well as some of them they give the monitoring capabilities so that we can continuously monitor the data drift or outlier detections once the model has been deployed into production. Yeah, so now I'll talk more about the architecture of the Dyna.MLOps framework that we have implemented. And I'll discuss on each of the tools that we have used in the complete framework stack. So on a high level, this is a complete architecture. So the top stage is the experimentation or development stage. So this line separates these two stages. So the bottom portion is relevant to staging or production kind of an environment. So starting from the top, the initial stage is experimentation stage, as I mentioned in the first slide. So we are using DVC as well as GitHub for source code as well as data version control. So when in the experimentation stage, we are tracking the information of the metrics, hyperparameters, and additional metadata information using DVC Studio. So DVC Studio is also a open source as well as managed service. So for bigger teams greater than 5 members, it will be a managed service. So, but for smaller teams less than 5 members, it will be open source. So later on, once in the experimentation stage, once we decide upon which model to be used in production, we'll do the continuous integration of the source code with the GitHub, and data version control, we'll do it with the DVC. And the continuous integration, since we right now we are using source code control as GitHub, it also has GitHub Actions, which has similar features that Jenkins provides. So we are defining a workflow.yaml file in GitHub itself. So whenever there are any events that are getting triggered in GitHub, like commits or pull requests, the complete workflow.yaml file would get triggered, and it gets executed sequentially. So this is how we are able to accomplish the continuous integration stage. So coming to the next stage, that is the staging or production. So here we are mainly using Docker for packaging and deployment in Kubernetes. So we can use Airflow and MLflow for continuous training. So once the model is into production, it is very essential to keep it updated with the real-time data that is hitting the model, so that the model accuracy does not drop or degrade. So we can use Airflow and MLflow as an integration for continuous training to schedule the jobs frequently and continuously update the model according to the new data. And the feast has been used as a feature store. So feature store, as I mentioned in the first slide, uh, it is a, yeah, so here we can see the feature store. So it is bridging the gap between the data engineers as well as data scientists. So it maintains a repository of all the features that are being used for a particular use case. And it also helps us to maintain consistency between training phase as well as the serving phase. So if there are different kind of features that are coming in during the real-time production kind of a scenario, feature store will help us to maintain the consistency and remove the features which were not used in the training phase. So I'll be discussing on that later. And as I mentioned, the Airflow and MLflow, these two are being used together for continuous training. So yeah, the Airflow is also connected to Kafka. So Kafka is streaming the real-time data, and based on the schedules, like for 1 hour or 1 day, whatever the data that has been streamed by Kafka will be used by Airflow to update the model. So this automated pipeline is what the Airflow would execute to continuously update the model. So coming to the last phase. So Selden is a open source tool that would convert the ML projects into production grade REST APIs. So it would give us the endpoints so that it can be used to get the predictions. So Selden has also integrations to Alibi Explain and Alibi Detect. So once the model is into production, it would be important to explain why a particular prediction is made. And as I mentioned before, there would be outliers that would be hitting the model, and there would be change in the distributions as well. So Alibi Detect would give the capability to identify the outliers present in the data that is hitting the model at production. Later, we can monitor our particular model at production using these dashboards. So the Selden's metrics can be scraped by Prometheus, which would be further visualized in Grafana. So all the request logging kind of parameters, like the request latency, number of requests that are being hit per second to the model, all those can be visualized in real time with Grafana. And whatever the data that is being streamed by Kafka, it would be stored in Elasticsearch, and we would be visualizing that in Kibana dashboards. So Kibana dashboard, we can basically use it to visualize the data distributions that is being streamed by Kafka. So this is the MLOps specific AWS architecture. So almost everything is the same with respect to the previous slide. So the only difference is the way we have implemented the complete MLOps stack in AWS cloud. So the initial model experiments, as I discussed in the previous slide, it includes all these data version and source code version control with the continuous integration. The model deployment phase, it has the continuous deployment. So we are using OpenShift to prepare the Docker images. So later on, once the Docker images are prepared, they are being stored in a Docker registry, which is a centralized repository to store all the Docker images. Later on, these Docker images are being picked up by Selden, and it is getting deployed on Kubernetes engine, that is Amazon's EKS service, Elastic Kubernetes service. And there are two set of models here. So one is the predictor model, and the second one is the explainer model. So once the model has been deployed into production, we would be initially sending the instance to prediction API, which would give us the prediction for that particular model. And later on, we are sending the same instance to explainer model as well, so that it would be able to explain why a particular prediction has been made. And later on, as I discussed, all these dashboards are being used to continuously monitor the data as well as the requests that are being hit the model. So from here on, I'll be discussing in brief on each of the tools that we have used as mentioned in the previous two slides. The first one is data version control. So similar to source code version control, that is a Git, DVC is used to version control the ML model data and to reproduce experiments across different data versions. And also DVC can be used to tune the hyperparameters as well. So in the picture below, we can see the commands which are almost similar to Git. So in Git, we already know these two popular commands. So the code which is residing in our local system, whenever we Git push it, we can push the latest code into the remote Git servers. And if you want to fetch the latest code from the Git server, then we do a Git pull so that we can have a latest code in our local system. So similar to this, even in DVC, the commands are similar. The DVC push and the DVC pull. Suppose so this model.pkl, this is a model that we have trained, and to for reproducibility, we will be using the same model to deploy it into production. So this pickle file is being stored in one of the blob storages like S3 or Google Drives. So the data as well as the model files can be stored in the blob storages. And once we do the DVC pull or DVC push, we'll be able to send or fetch the new or latest versioned data or model files. So here the main difference is the DVC matches the right versions of data, code, as well as the models. So here the DVC is actually doing the data versioning through codification using the .dvc files. So this .dvc file actually integrates between the model file as well as the code. So if you want to find out, suppose for a particular version of the code, what kind of model has been trained and stored in DVC. So the integration is provided by this .dvc file. So this .dvc file would be for this model.pkl file would be stored actually in the Git server. So whenever you pull the latest code and execute, so the model like the code has to know what version of the data was actually stored in the DVC. So this is a .dvc file which has the information hashing information of the locations in which a particular data or model file has been stored in the blob storage. So whenever you execute a particular version of the code, it will actually fetch the equivalent version of the data that was used from the DVC remote storages. So in this particular diagram, we can see the commits that have been made. So in each of these commits, there has been a change in either the features or the input parameters, or even there are some updates on the data set as well. So as I mentioned in this particular diagram, even if there are any versions of data that has been used, we can easily keep track of it, and we can do the version control of the data as well. So these are some of the equivalents of DVC, that is a Delta Lake, Git LFS, Pachyderm, DALT, and LakeFS. So there are multiple tools that are available apart from DVC. But based on this chart, we selected DVC because it is obviously open source, data format agnostic, and DVC also supports the cloud blob storages like S3, Google storage buckets, as well as Google Drive. And later on, it is also simple to use. It has a lot more features when compared to Git LFS. So that is why we used DVC as a tool for data version control. So GitHub Actions, as I mentioned in the architecture diagram, GitHub Actions was used as a continuous integration tool. The equivalent of this will be Jenkins. But instead of using a third-party tool, we thought of using GitHub Actions itself, since we are using GitHub for source code version control. So here, as I mentioned before, we can define a workflow.yaml file, which includes the steps that it has to execute once the code has been merged into GitHub repository. So as soon as as mentioned below, these are the different kind of triggers that would trigger the workflow.yaml file, which would execute sequentially. So we can actually specify which kind of trigger should actually execute the workflow.yaml file. So it can be a push or a pull request, or we can, whenever there is a tag that is getting created, or whenever a new branch is getting created in a GitHub repository. So we can identify these kind of events and mention it in the workflow.yaml file. So whenever these events occur, the complete YAML file would get executed, and the continuous integration would be done using GitHub Actions. Later on, moving to continuous machine learning. So this CML is a CI/CD tool specifically for machine learning based projects. So basically, the CML is an open source library to implement a CI/CD for ML projects, and to automate development workflow, including model training and evaluation. Comparing the ML experiments across a project history can also be made using CML. And CML has integrations to DVC as well as GitHub Actions. So in the diagrams, in these pictures, we can see its integrations to DVC, TensorBoard, and we can also host our own cloud runners, cloud runner instances, and mention the information of the credentials in the workflow.yaml file. So whenever a particular workflow gets triggered, it would execute on the runner that we have defined, such as suppose AWS EC2 instance with GPU support. So in this diagram, we can see if the training requires a GPU support, we can use the CML for that and define all the steps in the workflow.yaml file. So these steps that are being shown is the YAML file that GitHub Actions uses. So here you can see some of the commands that DVC is using to reproduce a particular experiment, that is a DVC repro. So whenever this particular command gets executed, whatever the model has been defined in the DAG of DVC, the complete DAG would get executed sequentially and a particular experiment would be reproduced using this DVC repro. And later on, if there are multiple experiments that we do, if you want to visualize what is the change in the metric or the end output across all these experiments, we can view it using a CML's a command line interface. So here you can see the image of style transfer between the experiment which is in workspace with respect to the experiment which was executed in the master. So this is how it differs across various workspaces. And it also gives us the information on the Cloud Runner's GPU instance, and as well what is the old parameter that we used and the new parameter that we have used across these two different workspaces. So here I'll be discussing more on the ML flow. So ML flow can be used in the experimentation stage as well as continuous training stage. So ML flow is basically used to track the machine learning experiments. So in the experiment phase, suppose we are exploring a different kind of models. Suppose a decision tree based random forest or gradient boosting or XGBoost or a logistic regression. So if we do not know which kind of model would be a best suit for the data that we have, so in the experimentation stage, it would be essential to keep track of the experiments that we are conducting and what all hyperparameters as well as metrics that we were able to achieve in each of these experiments. So MLflow as a tracking tool, we can use the MLflow tracking based feature. And later on, it has additional features like MLflow projects, MLflow registry, and MLflow models, which I'll be discussing in the coming slides. Yeah, so before moving further on the features, here I'll discuss more on the architecture behind MLflow. So in the diagram, we can see the code that we are using to experiment any ML-based project. So it will be in the local host. We are trying to set up the tracking server of MLflow in a remote host, suppose EC2 instance. So the tracking server, which is hosted on EC2 instance, would be further connected to PostgreSQL database, which is also a remote host, and also to store the model's artifacts like the pickle files and all. It is essential to have a blob kind of a storage. So the remote host, which is having the tracking server, would also be having the information of where the model artifacts are getting stored. Suppose that is the S3 buckets. So initially, whenever the MLflow client in the local host, it would get triggered based on the code that we are executing. It would send a REST API request to log the MLflow entities to the tracking server. So the tracking server would connect to the remote host to insert MLflow entities into the database. So all the metadata kind of information like hyperparameters or metrics, these informations for a particular experiment would be tracked by the server by storing it into the Postgres SQL database. And later on, if once we want to save the model in the blob storage, the MLflow client sends a REST API request to fetch the artifact storage URI location, so which would be present in the configuration of tracking server. The tracking server later responds with a URI of the S3's artifact store, where the local host would connect and upload the complete ML models artifacts into the S3 bucket on the specified URI location. So this is how a remote tracking server with artifact store as well as a PostgreSQL based database would look like when we set up MLflow. So coming to some of the features of MLflow, that is MLflow tracking and MLflow project. So as I mentioned before, the MLflow tracking, so it might be in the Jupyter notebooks or any kind of IDEs that we are executing in our local host. We can track each and every metric that has been used. with respect to by using MLflow's tracking server. So here we can see the parameters, metrics, artifacts, metadata, and model. All these would be tracked, and it has a UI as well as a API support. And the MLflow project, it is a format to package the data science code in a reusable and reproducible way. So the complete project can be actually packaged, and it can be deployed in any of the Docker images as well as the local systems, so that anyone in the team can be able to reproduce a particular experiment based on the dependencies. Yeah, so these are some of the available open source as well as managed tools to track the experiments. So some of the features for polyaxon or sacred, so it might be like additional to whatever MLflow provides. So polyaxon has additional support where we can train and monitor the models as well when compared to MLflow. So these are some of the other alternatives that can be used to track the experiments or the ML models during experimentation stage. Weights and biases is a managed kind of service, and it has a lot of additional features apart from whatever MLflow provides. Yeah, so as I mentioned in the first slide about the feature store, so Feast is a open source feature store that would help the machine learning teams to define, manage, as well as validate the features which are going to be served to the models at production. So usually the features which are being used for a particular ML project, the Feast would be able to share all these features across different teams, and we can also use the features across multiple projects using the feature store. So this is why this is what the capability of a feature store is, and that is why we need a feature store. So as I mentioned in the first slide, there would be a lot of teams. So obviously a data scientist would be connecting with a data engineer who is responsible in getting the data. So a feature store would be a bridge between a data engineer as well as a data scientist. So the feature store Feast can also serve feature data to models from a low latency online store or from a offline store that will be used for model training. So the online store is something kind of a low latency, high throughput kind of a database, such as Redis. The AWS equivalent of Redis is Elastic Cache. And offline store would be something like a BigQuery or a Redshift kind of a database, where we would be storing the all historical kind of data, which would be further used to train the model. So these are two stores, like online store and offline store. These features are also provided by Feast to serve the feature data to models. So here we can see the streaming sources. So if we are getting the real-time streaming data from Kafka, it would be routed to Feast feature store, where it has all these capabilities to store, transform, serve the features, and validation and monitoring of these features. So all these can be achieved using Feast. And data scientist, he would be fetching all the historical data using Feast, which would be connected to the batch sources like BigQuery or Redshift to train the model. Once the model is trained and deployed, Feast will again come into picture, where it has integrations to the continuous real-time streaming data from Kafka. So as I mentioned before, Feast feature store maintains consistency between training as well as serving the features. So in the production stage, if we are having a different kind of features that are being sent by Kafka to the model, the feature store like Feast would help us to maintain the consistency by removing the additional features which are not used in the training phase. So this is the process diagram, how the feature store Feast would work. So initially, we would be creating a feature table where we would define all the features that are going to be used for a particular model training. And later on, based on the feature table, all the values with respect to each and every feature is being ingested into the feature table, and it is being stored in BigQuery or Redshift database. Later on, this data is being fetched to train the model in the training phase, and this can be even materialized or loaded to the online store like Redis, so that we can serve the data that has been stored in online store and get the predictions for them. These are some of the feast components. So the architecture diagram, which essentially sums up whatever I was discussing before. There is an offline store and an online store. If you want to transfer some of the data from offline store to the online store, it has the feast provides a SDK, which would help us to do the loading of data from offline to online stores. So in the offline store, we would be storing the historical data, which would be fetched by the data scientist to train the model. And later on, once the model has been trained, we would be deploying it. And here we are connecting the online store, that is the data that has been streamed by Kafka and is stored in online store, that is a Redis or a DynamoDB kind of a database. So this would be connected to the model which is deployed at production to get the online features. And later on, the model at production would be giving us a prediction based on the online feature. So once the model is into production, so it is very important to interpret as well as explain a model's prediction. So it is the only way to find out whether a model has learned in a proper way or not by using the explainability or interpretability. We cannot always expect a data scientist to have domain knowledge of the use case. So explainer model would bridge the gap between a domain expert and an ML engineer, which would help us to evaluate models' learnability and its feasibility at production. So in the as mentioned in the slide, we can the explainability would help us to answer these kind of questions like why did not a particular treatment work on a patient, or why a particular loan was rejected. So the explaining these kind of scenarios at production is very important. So Alibi, as I mentioned in the architecture slide, I'll be again moving on to it. Yeah, so in this architecture slide, as I mentioned before, Selden has integrations to the explainer as well as outlier detection models. That is Alibi detect and Alibi explain. So I'll be discussing on the explainability part right now. Yeah, so Alibi is a open source Python library for models inspection as well as interpretation. So it provides high quality implementations of local as well as global explanations for classification and regression models. So there are a couple of algorithms that are supported by Alibi for explainer models. That is kernel shape, accumulated local effects, anchors, contrastive explanation methods, and integrated gradients. I'll be explaining some of these in the coming slides. So the first one is the kernel SHAP algorithm. It provides model agnostic human interpretable explanations which are suitable for mainly regression as well as classification models. So SHAP is mainly used on the use cases which are working on tabular data, like the time series kind of models or regression based models. So in the below diagrams, we can see how the SHAP will be able to SHAP will try to explain a particular model's prediction. So for this use case, suppose these are the various features, and we can see the SHAP value, whether it is a positive or negative with respect to the model output. So if it is moving in the red side, so it means a particular feature is having a higher contributions or higher SHAP values, which will be further influencing the model's output. So if it is on the blue side, then it means a particular feature is having less impact on the particular output. So in the middle picture, we can see amina flow and the average flotation airflow. So these two are the top two features which are highly impacting the model's output. And in the last diagram, we can see a particular model's output, how it has varied with respect to each of these features. So here we saw that amina flow and average flotation airflow, these two are having higher feature importances. So similarly, we can see the same which is getting reflected in this last diagram as well. So the amina flow, so there is a large shift, as well average flotation airflow, there is a large shift. So with respect to the average models output, how each of these individual features are affecting the end output is what being interpreted in this particular diagram. So if there is a positive SHAP value, it will be impacting on the positive side, or if it is a negative SHAP value for a particular feature, it will be impacting on the negative side. So the next one is CEM, that is a contrastive explanation method. So CEM generates instance-based local explanations similar to LIME for classification as well as regression kind of data sets. So it basically gives these two factors, that is pertinent positives as well as pertinent negatives. So in this diagram, suppose the example is the first image is 3, the actual prediction would be 3. So the pertinent positive that is given by CEM. So here we can see what kind of features are sufficient to decide whether this is a 3 or not. So here we can see the blue patches which are embedded on this particular picture. So based on these blue patches, it is sufficient for the model to detect it as a original label, that is 3. So that is the pertinent positive. So it also has a capability to give a pertinent negative. So what is pertinent negative? So in this particular diagram, you can see if there is a horizontal line which is mentioned in this pink color. So if this particular line was there, then it would have predicted this image as 5. So that is what pertinent negative says. So it actually tells the absence of a particular pixels, which is essential for final classification, that is 3. So CEM is mainly used to explain the deep neural networks based classification kind of models. Moving ahead, this is the another algorithm, that is integrated gradients. So integrated gradients, it gives an importance value to each input feature based on the gradients of the model's output with respect to the input. So suppose this is a NLP use case. So we can use integrated gradients to any regression as well as a classification based use cases. So in this NLP use case, suppose this is a classification kind of use case. So here we can see the import a gradient. If a gradient for a particular input feature is higher, then it would be denoted in a green color. If it is lower, then it would be denoted in the pink color. So here the words with a higher positive attribution are highlighted in shades of green, and the words with the negative attributions are shades of pink. So suppose this whole use case was about predicting the sentiment of a particular sentence, then it would sum up and tell you the explanation on based on what entities the total prediction was positive, or based on what entities that prediction was negative, the negative sentiment or a positive sentiment. So going ahead, so this is the event-driven system, that is Kafka. So I'll touch upon the architecture slide again, so that the audience are not lost. So here we can see the Kafka, which is connected to Airflow, so that the live streaming happens, as well as the continuous training of the model happens. So I'll be touching upon the Kafka right now. Yeah, so Kafka, so models at production are connected to event-driven systems like Kafka to continuously send the real-time data to hit the model, and also to get the predictions. So in this diagram, use the pointer. Yeah, so here we can see the streaming data from different sources like IoT devices, mobile devices, or edge devices, or from databases or data lakes are getting streamed using Apache Kafka. So we can use this kind of event-driven system in order to mimic the continuous training process in the MLOps pipeline. So these are some of the components which Kafka uses. That is producer, consumer, as well as Kafka brokers. So a Kafka broker is nothing but a server. So it would be like an intermediary which would exchange the messages between a producer as well as a consumer. So producer would basically act as a sender. So whatever the data that is being sent by suppose edge devices or IoT devices are collected by producer and are sent to the Kafka brokers. Later on, the consumers would consume the data that has been collected by Kafka producers, and it would be on the downstream used to visualize on any kind of dashboards on the data that has been collected, or any kind of a reporting or a dashboards using Power BI, or gathering the insights for the business. So all these things can be achieved using Kafka's real-time streaming data. So we are actually integrating Kafka with Airflow, as well Kibana dashboard. So as I mentioned in the starting slide of the architecture diagram, we are also visualizing the data distributions in which the Kafka is able to stream the real-time data. So here we can see the data source, which is connected to Kafka producer. Later on, all these data is getting collected and stored in the Kafka topic. So based on the Kafka consumer, it would, based on the permissions, it would connect with Kafka topic and gather all the newly streamed data from Kafka producer. And this particular real-time data is actually what hitting the Selden's ML model at production. So the data, real-time data streamed by Kafka is hitting the ML model at production in order to get the predictions. And later, we can store the data distributions that are being streamed by Kafka using Kibana dashboards. And also we can see how the model has predicted over time using Kibana dashboards. So this is a deck on Selden course deployments with CI and CD. So as I mentioned in the architecture diagram, we are using a Selden core and a Selden deploy in order to convert a particular ML project into a production grade REST API. So here we can see how the complete orchestration is getting maintained using Alibi, Selden, as well as Kubernetes. So here, as mentioned before, we have two models, that is explanation model as well as prediction model. So whenever a particular request is getting hit from any kind of device, we would initially get the predictions from this prediction API, and later we would get the explanations from the explainer API. So the Sheldon core, initially it would create a explainer model, and it would deploy it on a Kubernetes cluster. And also it would parallelly deploy the prediction model. So the prediction model can be from any of these frameworks like TensorFlow or XGBoost or PyTorch or scikit-learn. So once these two models are deployed using Sheldon deploy into Kubernetes cluster, we can also push the relevant code into GitHub, so that whenever some changes happen to either the prediction model or explainer model in the source code, we can continuously do the integration using GitHub Actions and deploy it using continuous deployment. So this is how the cycle goes: the creation stage, and later on deployment stage, and the continuous updations are happening like this. And also we can scrape the Sheldon metrics and see the request or request logging or metrics using Prometheus and Grafana, as well as Elasticsearch. So finally, so this is a continuous training tool that we were using, as I mentioned in the architecture diagram, that is Apache Airflow. So Airflow is a platform basically used to schedule and monitor the workflows. So here we can see a particular workflow that has been defined in this particular diagram. So each of these component in the workflow are tasks. So whenever a Airflow would scheduler would get triggered, each of these tasks in the particular directed acyclic graph would get executed sequentially. So this is the architecture diagram for Airflow. So it has a user interface, which so whenever a user triggers a particular event on web server, the web server would further send this information to the scheduler. So the scheduler would take up the all the DAG information that has been mentioned at the top, and it would be sending it to the executor. So all the metadata information would be stored in a database, which the scheduler would be having access to. So whenever there is a trigger that is happening, scheduler would fetch all this metadata information from the database and sends it to the executor. So executor will be having the access to the directed acyclic graph. So that is mentioned at the top. So it would pick up this particular graph, and it would execute each of them sequentially on the worker nodes. So this is how Apache Airflow can be used to continuously train the model at regular intervals that we have configured. These are some of the use cases across ERS verticals, which can be actually used to implement the MLOps that we have designed. So across the various ERS verticals like industrial, medical, auto, telecom, aero, and semiconductor. So most of these use cases can be used, and we can mimic all these use cases on the MLOps framework that we have built in. Yeah. So coming to the demo, so this is how the UI of Dyna.MLOps framework looks like. So before touching on the demo, I'll give a brief on the use case description. So the use case for which we have implemented MLOps is a production optimization based use case. So here the main objective is to predict the impurities in iron ore so that we can maximize the iron production and minimize silica waste. So in the diagram, we can see this is a froth flotation process that is happening in production optimization. So initially, we'll be having a mixture of iron ore and silica that are fed to this flotation tank. This agitator will rotate and disperse air into this tank. So here we can see the air bubbles that are getting dispersed by the agitator. So later on, since iron is a water repellent, it is carried to the surface by air bubbles. So here you can see the air bubble, it is carrying the iron to the top. Later on, the froth will float to the surface of the tank, and it would get collected in a separate tank. So finally, here we can see the separation of iron as well as the silica in two separate containers. which is the end output of a froth flotation process. So here the objective is to predict how much silica is getting separated from the froth flotation process. So this is the description of the data set that we had. We had these features like a percentage iron feed, percentage silica feed. All these are the inputs, and the last one, which is the percentage silica concentration, is the one we are targeting to predict from the ML model. So some of these features like a starch flow, amina flow, over pulp pH, over pulp density. So all these actually help and contribute towards the separation of iron from silica. So these reagents would help to increase the productivity of froth flotation process by increasing the separation of iron as well as silica. So based on the data set, this was how the model had performed. So this is the learning curve for training as well as a validation data set. This is how the mean square error has converged, and the R square correlation of correlation coefficient, it is 0.84. So we are using this particular model to mimic the complete MLOps based framework that I have discussed right now. So I'll be showing the demo. Yeah, so this is a landing page, and this is the architecture as I had shown in the deck. So when I go to the production optimization based use case, so in the introduction, we can see all the details of the features which was mentioned in the slides. So coming to the model's experimentation stage. So this is a DVC Studio, which is used to track the experiments that we have done. Suppose, so here these are the different commits that have been pushed to the GitHub repository. And so here we can see the details of the parameters as well as metrics for each and every commit. So there is a difference in the mean square error over here. So 0.77 and it is 0.83 for these commits. And since DVC Studio has integrations to data version control as well as source code version control, here we can see what kind of files are getting changed over time across different commits. So this is a raw data, this is a pre-processed data. So what is the size of each of these data which is getting triggered? And later on here we can see at the last the hyperparameters for the gradient boosting model, the learning rate, the minimum depth, minimum number of samples in a particular leaf. So all these are the hyperparameters that are being used for these different experiments. So here suppose I click on a particular commit and run it. So here we can see different hyperparameters that we are able to tune. So here I can change some of these parameters and create a new branch and commit those changes. So once I do this commit, the workflow.yaml file would get triggered, and the complete experimentation stage of pre-processing, training and validation would get executed using GitHub Actions and continuous machine learning. So once the experiment has been completed, we can see the report of continuous machine learning over here itself. So here you can see the icon. So if I click on this, so here we can see what all changes I have made for a particular commit. So here you can see I have increased the number of trees and decreased the learning rate. So this table sums up what was the old metric and what is a new metric for the particular commit that I have made, and what is the change. And these are the deviance plots for those two models. Deviance plot, feature importance plot, and the learning curves, how it has converged for the mean square error and R square. So all these plots can be actually mentioned in the markdown file, and we can view it in the GitHub repository itself. So based on these charts, suppose APR can be raised, and the manager can review it, and if it is performing well, he can accept the PR and merge it to production, so that the complete CI/CD can be orchestrated using this particular tool. So coming to the model deployment phase. So this is how the data set looks like with all these individual features. So if I select on a particular row, we will be able to get the prediction. So this is the percentage of silica that is that will be able to separate from this particular entity. And at the bottom, we can see the explainer, that is a kernel chap explainer. So how each of these features are contributing to the end output. So all these features in red are contributing higher to the end output, that is a silica concentration. And the blue ones would be contributing lower to the silica concentration output. And as I mentioned, once the model is deployed into production, we can view all the metrics, the request logging metrics using Grafana. So here we can see how the model has how many requests are being hit to this particular model which has been deployed in Kubernetes. So we have two models, that is the explainer model and production optimization prediction model. So the number of requests as well as the latency for each of these models can be viewed using these dashboards. And later on, since we have connected Kibana with Kafka, we will be able to view the data distributions as well. So suppose, so here we can see the data that has been streamed by Kafka, and which are getting stored in Elasticsearch, and we are using them to visualize in Kibana dashboards. So this is the output of the model, that is a silica prediction. So this is how it has varied every 30 seconds, so from 11:30 to 12:20. So this is how the live streaming data can be visualized using Kibana dashboards. So these are the other set of features. Whenever it has been streamed, we can see what kind of distributions or variations it had for each of the individual features. So we can also plot historical histograms for each of the features to visualize on what particular range a particular feature value has frequently come in using Kafka. So the continuous training, since we have achieved it using Airflow, so here we have this particular Airflow, whatever I'm showing, it has not been implemented for production optimization. So just to show the continuous training how it works, I'm showing this particular demo. So here we can see these three phases, that is the initial model DAG, the streaming DAG, and the update DAG. So initial model DAG, it would be executed only once. So here we can see the schedules. So once we have a initial model that would be created using the initial model tag. Later on, for every 5 minutes, as mentioned in this schedule, the data is getting streamed. So it would be stored in a particular folder, whatever the data that has been streamed using the stream tag. And later on, for every hour, whatever the data that has been streamed in the previous 1 hour would be used to continuously update or train the model. So if the new model has performed better than the current model, then it would be replaced in the production. So here you can see totally right now 12 updations have been made using update tag. Suppose if I click on this, you can see, so this is the DAG, which is having the steps like get the data from Kafka, load it, next pre-process it, and later use the same data to update the model by training it. So, and if there is a any change in the model, then the previous model would be send it to the archive directory. So these are the various phases that would get triggered for a continuous training kind of a procedure using Airflow. So we can also view the logs at each and every stage. So this would be helpful to debug if there are any errors that are occurring. So here you can see the model training logs, how the accuracy is improving over each and every epoch. So later we can track the experiments that are being conducted using Airflow, using MLflow. So here, as I mentioned in the Airflow, we had 11 retraining procedures that had been triggered till now. So in MLflow UI, we can compare all these 11, how the model has updated over time. So here you can see from morning 11:35 for every 1 hour intervals, the retraining has happened. And you can see the amount of data that is being used to update each and every model, and what is the accuracy of the current model, and what is the accuracy of the updated model. So if since here there is a marginal improvement of the accuracy with respect to the current model, this is being used in deployment or production. So later on the same is getting updated. So here we can see an incremental increase in the output of accuracy. So it has increased from 0.58 to 0.83 in the past 10 hours due to the incremental training procedure for the data that has been streamed using Kafka. So this is how we can keep a check on the data that is coming in, and we can continuously update the models. And later on, since I talked about Feast, so we can use DynamoDB as an online store to fetch the records from Kafka, and later on storing it into the low latency, high throughput kind of a database. So here, if I click on view items, so here you can see each of these entities, as I mentioned in the deck. These are the various features that are getting streamed using Kafka, and later they are getting stored in DynamoDB database. Yeah, so that's it I had. So I would request everyone to give a feedback on the link that has been shared in the chat. I would be open to take
Thanks,
any questions.
Shreyas. We have a lot of questions in the chat window. So
Okay.
I'll invite folks to ask questions directly since some of them might have been answered in the demo itself. So, Kartikeya, you have asked quite a few questions. Do you want to go ahead? Any question for Shreyas? You can unmute yourself.
I have a question. I need to run off, Uttara, if I can ask
Sure, sure.
Shreyas.
Please go ahead. Please go ahead.
Hey, Shreyas, thank you. This was very informative. This is Vasu here. See, one of the key things, right, in terms of an MLOps perspective is the deployment capability to say that today I want to, let's say, deploy it in GCP, and tomorrow I would want to, let's say, deploy, or I would want to do a scale up, scale down. I mean, apart from whatever you spoke about the deployment, while you spoke about saying we have deployed this in Dockers, in Kubernetes, and so on, the key capability, if you have seen demos of Velohai or any other COTS product, right, it's the key capability to give the ML engineer the automation to say where do you want to deploy, how do you scale up, scale down, right, and so on and so forth. While you spoke about a lot of that in the PPT when we demonstrated, right, we did not talk about how do you give that capability to back to let's say an ML engineer who defines the ML flow pipeline, the ability to go back and deployment and decide on where to deploy and so on.
Yes, thank you for this question. So, yeah, we have actually we are trying to expand this particular framework to different cloud providers as well. So
Okay,
right now it is limited to AWS, but obviously, if you want to keep it agnostic to different cloud providers, the main thing that would differ is the credentials that we provide for to access the infrastructure of each of these cloud providers. So definitely, we would be able to do that once we expand this to different cloud providers.
perfect. I will send you the recording. I don't know whether you have seen well. So we have signed up the partnership also.
Okay.
So they have given within the user experience a drop
Hmm.
down which gives you to register different sets of these, let's say, instances, and lets the user go back and select all of that. So I think that could be a good capability to build that. And last question is, we are calling this as Dyna, but end of day we are using ML flow, right, behind the scene from an MLOps standpoint for building ML pipeline. But I understand that we are bringing in multiple other things like the feature store, the fees part, and all of those, and that's why we have given a name called Dyna, right? Is that a correct understanding?
No, actually, frankly speaking, we do not have any background behind selecting Dyna as the framework's name. So there
No,
is,
but
yeah,
yeah, but it's our name, right? I mean, we have just given a name called
yes,
Dyna, but what I'm
yes,
saying is, end of day, if you really look at it, we have integrated all of these and sort of given a reference architecture to customer, right? So that when they bring in so many components, we are saying that we have done that before, and thereby we can help you do that much faster, right?
okay,
That's our point of view,
sure,
isn't
sure,
it?
sure.
Okay, so you didn't touch upon the ML flow pipeline as such, right? In the demo, did we go through
I
that?
showed it the ML flow, like how we are able to track the experiments, right?
Correct, the track, but the overall pipeline building itself, where you drag and drop or bring these components together, I believe ML flow itself gives you the capability to build the ML pipeline.
Yeah, it is it has limited features, but as I discussed in the architecture, right, there are a lot
Hmm.
more capabilities that we need to integrate in the complete MLOps pipeline. So,
Hmm.
with respect to that, we cannot alone use MLflow as a complete ML ops kind of orchestration tool. So,
Hmm.
obviously, we can use it for tracking as well as packaging for reproducibility, but we cannot use it anymore other than these features.
Okay, got it. So, Shreyas, I've set up a meeting in your morning time with Kamesh also. We'll discuss on one of the other opportunity where we want to present a holistic view.
Okay,
We'll take some of these what you presented, right? Very good one, and with a demo, it will really be helpful.
sure.
If yeah, thank you,
Yeah,
Shreyas.
yeah. Thank
Thanks
you.
for that.
Thanks, Vasu. So there
Thank you.
was a question, Shreyas, it's from Akash, and the question is, what is the significance of dip in hype curve after ML ops?
Where is the question? I see a lot of questions are there.
So, do you have any comments on this one?
Okay, let me go back to the slide. Is the slide being shared or?
No, not anymore.
Okay. Yeah, is it visible now?
It's loading.
Yeah, it is visible now.
Okay.
Yeah, yeah. Can you repeat the question?
Yeah. So, what is the significance of dip in hype curve after ML ops? So, wherever I guess
Oh,
ML
okay,
ops is
okay,
written.
okay. So usually this particular phase, so whatever the expectations that a particular technology would have raised, right? So it would peak at a particular point of time, and later on, since a lot of experimentations has to be done on a particular technology for the viability of it for larger adoption. So that is where this particular phase of trough of disillusionment will come. So it doesn't mean that every technology will go into this phase, but a lot more will this dip is actually seen since a particular technology was not able to meet the expectations it would have set in the previous phases. So that is where this dip will come up in the hype cycle.
So this dip is coming after introducing MLOps, or
No. This is not with respect to MLOps. So the hype cycle given by Gartner, it is across various different technologies and verticals as well. So this based on whatever the new technologies that would come in every year, right? So this hype cycle would basically tell you. Here at the bottom we can see the color coding, right? So
Yeah.
for a particular technology, how much time it might take in order to get stabilized and get matured. So once a particular technology reaches the slope of enlightenment or plateau of productivity, it means that the technology is being adopted by a larger audience. So that is where the technology will become mature. So in the color coding, you can see for each of these technologies, how much time on an average it might take for a larger adoption. So it is not dependent on MLOps. So here you can see there are a lot of tools, right?
yeah.
So each of these tools would actually end up in each of these phases with respect to the time that has been defined at the bottom.
Mhm.
So, Shreyas, next question is from Naresh. Airflow and MLflow are fully automated tools.
Mm, fully automated tools in the sense. So
Naresh, can you clarify? Are you there on call? No, I don't see him on call anymore. So we'll move on to next question, Shreyas. Maybe we
yeah,
can clarify later.
yeah.
Okay. So there is a question from Kalpesh. For alibi detect, do we need to provide some statistics to detect outlier or is it automatic?
Yes, these alibi detect and explain, both of these, like for explainer, I discussed different algorithms. Similarly, even for outlier detection, we have a lot of algorithms. So whichever algorithm we feel is suitable for our use case, we need to train it and deploy it using Seldon onto this Kubernetes engine. So after that, once we deploy it on Kubernetes engine, everything will be automated.
Okay. There's a question from, sorry, there are too many questions. Just a second. There's a question from Ravi. Are CVO and TMNL HCL case studies?
No, these are not any of these use cases that had discussed here. These are not HCL use cases. These are generic use cases that have been implemented by different financial or healthcare sectors.
Mhm. There's a question from Kartikeya S. Will MLflow handle many teams trying to solve same business problem?
Yes, obviously, this is an integration between different teams, as I kept on mentioning several times in the discussion as well. This is an integration between data engineering, data science, as well as the DevOps teams. So obviously, all these teams should be involved so that the complete MLOps pipeline is built.
Mhm. Okay. Dheeraj is asking if it is mandatory to use feature store in Dyna.MLOps framework.
So obviously, if data engineers and data scientists are in this particular project, then a feature store would definitely benefit. So as I mentioned, the importance of a feature store is to maintain the consistency between the training as well as the serving. As well, we can use the features, the reusability of the features across the different projects and different teams. So if there are multiple teams, it is obvious that we would require a feature store to have a better management of what kind of features each and every team is continuously updating. And yeah, that sums up the question that has been asked.
Mhm.
Okay, just to follow up, is it mandatory? Like, can I skip
No,
that
no.
story?
See, any of the tool that I have mentioned in this architecture is not mandatory. So it is up to you to choose which tool you want in your MLOps framework to be deployed for your particular use case. So since this is an open source stack, so based on the use case, you are able to decide which one do you want and which you do not want.
Oh, okay. So doesn't Dyna MLOps does provide me a one-stop solution for all this framework?
So this actually is a continuously evolving framework. So right now, whatever the architecture that I have shown, it includes all this capability. So obviously, if you are using this particular framework, since this is an open source, that was the point that I was mentioning. So since this is an open source pipeline, you can plug in or plug out any particular tool. But if you are using Dyna.mlops, all these would be involved for your use case.
Yeah, so that means if I use Dyna MLOps, I would need to use feature store and
Yes.
all
Yeah.
functionalities.
Yeah.
Okay, so I have a couple of more questions, Uttara, if I may ask.
Yeah, go ahead, please.
Okay, so one of the question was uh, can this framework be deployed in the where the production environment is on premises?
Yes, definitely. So we have used I have showed the demo for a particular internal use case, but definitely this can be used on premise.
Okay, so in that case, I guess we'll have to configure all these things on their premise and
Yeah.
then make it
Yes.
up.
Yes.
Okay,
Can I
and
ask you a follow-up question?
uh, just a second. I have one last question. What would be the learning curve to use these frameworks? I mean, do I need to understand and know about Airflow, DAG, writing DAG scripts?
No.
Such things?
So since if you are using this already built framework, there is no need to learn anything specific to each of these tools. But if you are developing it by yourself, obviously you need to go through all these 15 or 18 tools or technologies that have been used in the architecture.
But if I need to modify any DAG pipeline,
Mhm.
I would need to write a new script, right?
Yeah, that's what. So we
Or
are
specific to my
we
data.
haven't yet given that particular capability so that the user can configure based on their custom use cases. So we are trying to give all those features in future.
Okay, so right now, what kind of data does it support? Only tabular data?
Yeah, tabular, and we are extending this to image as well as NLP based use cases in the coming month.
Okay.
So, Dheeraj, if you have follow-up questions, maybe have a offline discussion with
Sure.
Shreyas. We are moving towards concluding the session. Darish, do you have a question for Shreyas you wanted to ask?
Yeah, perfect. Thank
Yeah,
you.
please.
And sorry to interrupt you. For you mentioned we can deploy this workload on an on-prem. There are use cases for some of the clients dealing with super sensitive data where the environment is totally air-gapped. There is no internet connectivity at all. Can the solution be still deployed in those use cases? Back to you.
I could not understand this question completely. So there is no internet.
Right. I mean, the data center
Mhm.
pretty much is air gapped, means it has no connectivity to internet inbound or outbound. That it's due to the sensitivity of the data. They
Okay,
have no connectivity to the outside world.
understood.
Can the
Understood.
solution be still deployed?
So in that case, slight modifications might be required for this particular solution because this has been designed based on a generic kind of a use cases. So if there's something more specific is required for a particular project, that can still be configured.
Okay, thank you. This was a great presentation, by the way. Thanks. Thank you for sharing that. Back
Yeah,
to you.
thank
Thank
you.
you so much. And if you felt so, please write in the feedback too. I've shared the link on the chat window.
I did already.
All right. Oh, thank you so much. Okay.
Yes,
Thanks,
really
Shreyas.
nice session. Thanks.
Thank you. Thank you.
Yeah,
So,
thank you.
we will now have to conclude, though there are a lot of questions in the chat, and Shreyas will reply to all of them in the chat itself. Also, please feel free to reach out to Kamesh, Mehul, and Shreyas for any other questions that you have. Thank you so much for joining in. Thanks, Shreyas.
Yeah, thank you, Uttara. Thank you, everyone.
Thanks, Uttara, for arranging the session. Thank you.